Okay, let's jump right in. Welcome to this explainer, where we're going to completely shift your perspective. Instead of seeing Linux security as this chaotic, disconnected jumble of tools, we're going to look at it as a cohesive, 9-layer defense architecture. This is the very architecture powering the modern tech world right now. So if you've ever felt totally overwhelmed by the sheer number of security protocols and acronyms out there, don't worry. We're going to clear all of that up by putting it into a beautifully structured, step-by-step sequence. Here's a quick look at our agenda for today. First, an introduction to Linux security. Second, boot and identity verification. Third, permissions and advanced capabilities. Fourth, kernel, memory, and file system. Fifth, network and mandatory control. And finally, security in the AI era. All right, let's get into it. So how exactly does Linux protect itself? While simultaneously powering global cloud, Kubernetes, and AI infrastructures, it's a massive question, especially when a lot of folks mistakenly believe Linux security is just about setting up a basic firewall, configuring SSH, or maybe running fail-to-ban. And hey, while those are definitely helpful tools, they barely scratch the surface. To really understand how the world's most critical infrastructure actually stays secure against relentless real-world attacks, we've got to look way deeper into the system's core design. As our source material outlines, Linux security isn't just one magic software tool. It is an impenetrable, layered defense. We're talking about a system where an attacker literally has to break through 9 distinct, sequential barriers. Honestly, think of it less like a single locked door and more like an ancient, highly fortified castle. If a bad actor breaches one wall, they just drop right into another courtyard filled with guards. Every single layer exists specifically to backstop and protect the layer above it. Section 1. Boot and identity verification, the foundation of trust. Let's start at the very bottom, because if the fundamental hardware is compromised before the system even wakes up, well, the entire castle falls immediately, right? To prevent this, Secure Boot initiates a strictly enforced cryptographic sequence. The UEFI verifies the bootloader, which then verifies the kernel, which finally verifies the initramfs. And here's the kicker. The system will instantly refuse to boot if a single file in this chain has been maliciously altered. It's a hard binary check. Either the system is absolutely pristine or it shuts down to protect itself. No exceptions. This unbreakable starting point establishes what we call the root of trust. Without a root of trust, any security software you install later on is basically useless, because the environment it's running in could literally be lying to it. Establishing this trust leads us directly into our second layer, proving exactly who you are before you even touch anything on the system. At Layer 2, Linux essentially acts as a highly strict bouncer at the identity center. It doesn't just casually ask for a password. It uses robust, modular components like PAM, that's pluggable authentication modules, along with multi-factor authentication to rigorously verify user identity. So whether you're performing a local login or an SSH login from halfway across the world, this layer ensures a shell is never granted until your identity is absolutely 100% confirmed. Moving on to Section 2, permissions and advanced capabilities, moving beyond basic rights. Now, just because you made it past the bouncer, that doesn't mean you automatically get the keys to the VIP room, the vault, and the utility closet. Layer 3 relies on that classic, elegant Linux philosophy, everything is a file. This model strictly assigns read, write, and execute permissions, and it separates them out by the owner of the file, the group, and others. And for more complex nuanced needs, it employs fine-grained controls like SUID, SGID, the sticky bit, and access control lists to guarantee users only see and touch what they're explicitly authorized to handle. But here is where it gets really interesting. Layer 4 completely fractures that dangerous, old-school paradigm of an all-powerful root user. Historically, if an application needed special access, it was just handed root privileges, which was a massive security risk. Today, Linux splits that godlike power into dozens of highly granular capabilities. For example, giving an application capnetadmin lets it manage network interfaces, sure, but it still totally prevents it from reading your private files. It's a huge game changer. Section 3. Kernel, memory, and file system, the inner fortress. Now we are entering the true security core. This is where the most sophisticated attacks happen, and frankly, it's where Linux fights back the hardest. Layer 5 focuses on kernel security. Whenever an application wants to do something, say open a file or open a network port, it has to make a system call. Well, this layer intercepts those system calls before they ever even touch kernel objects. It uses Linux security modules to act as completely ruthless gatekeepers. Tools like SELinux, AppArmor, SMAC, and Landlock operate right here, silently evaluating every single request against incredibly strict security policies. But wait, what if a hacker tries to bypass all that software logic and attack the system's memory directly? To answer the terrifying problem of buffer overflow attacks, Layer 6 employs ASLR, NX bits, and stack canaries. These are just fascinating defenses. They literally scramble the memory layout every single time a program runs, and they will instantly kill compromised processes if they detect unauthorized code trying to execute in restricted data areas. The really crucial point to grasp here is that even if malware somehow slips onto the disk, despite everything we've already covered, Layer 7's file system security is waiting for it. By setting critical files to be completely immutable using tools like Chatcher, attackers simply cannot alter them, not even if they somehow got high-level privileges. Furthermore, strict mount options, like putting no exec on temporary folders, mean that even if a hacker uploads a malicious script, the file system itself just flat-out refuses to run it. Section 4. Network and Mandatory Control, the Final Walls. As we near the top of the stack, these final walls exist to secure all the communications flowing in and out. Layer 8 upgrades traditional routing and basic firewalls with high-efficiency, highly granular networking tools. The industry right now is rapidly moving away from older stuff like IP tables and shifting toward incredibly powerful technologies like eBPF and Cilium. These tools allow admins to inspect and secure network traffic at blazing speeds directly within the kernel. And that is absolutely crucial for securing the massive, complex traffic flows you see in modern Kubernetes clusters. Finally, Layer 9 introduces Mandatory Access Control, or MAC. This steps in exactly where traditional discretionary access control fails. See, under DAC, a compromised root user could still wreak total havoc. But mandatory access control acts as the overriding absolute law of the land. It ensures that even if an attacker completely compromises the root user, their malicious actions are still firmly blocked if they violate the predefined mandatory policies. This flow brilliantly illustrates how mandatory access control actually works in practice, specifically when we look at SLinux. By strictly checking every single system call against predefined SLinux policies before allowing or denying the action, this flow forms the ultimate, unbypassable defense layer. Listen, it doesn't care who you claim to be. It only cares if the explicit policy allows the specific action. If you take a step back and look at it, this entire 9-layer stack exists for one reason: to enforce the golden rule of cybersecurity, the principle of least privilege. By systematically layering hardware checks, identity verification, granular capabilities, memory protections, and mandatory access controls, Linux proves that in a properly configured system, no user, application, or container ever gets a blank check. Ever. Section 5. Security in the AI era. Why this entire stack matters. So let's bring it all home. Why does this matter to you right now? How does this layered Matryoshka doll of security apply to the bleeding edge of modern cloud and artificial intelligence technology? Well, it is vital to grasp this one fact. Containers are not virtual machines. They don't have their own isolated operating system. They actually share the underlying Linux kernel. Because of this, Linux security literally is container and Kubernetes security. Container isolation relies entirely on Linux primitives like namespaces and cgroups. If the core Linux kernel is breached, that boundary just disappears, and every single container on that node falls. And when we scale this up to today's AI infrastructure, the stakes are astronomical. From the massive GPU clusters crunching petabytes of data to the incredibly high-speed InfiniBand networks connecting them, this entire ecosystem runs almost exclusively on this exact Linux stack. This means we aren't just protecting a single server or some simple website anymore. We are actively securing the multi-billion-dollar foundation of the entire AI revolution. The crucial takeaway from our source material today is that true security is an orchestrated synergy. It's hardware, identity, memory, network, and policy defenses all working as one. No single layer is impenetrable on its own, for sure. But woven together, they create a fortress capable of safely hosting the world's most sensitive and demanding workloads. But I want to leave you with a thought as we look toward a fascinating, rapidly approaching future of autonomous AI agents and real-time eBPF monitoring. You really have to wonder, are we building a fortress that will eventually learn to manage its own locks? As AI becomes capable of writing its own security policies on the fly, the intersection of Linux architecture and artificial intelligence is undoubtedly going to be the most critical battleground in tech. Definitely something to keep in mind the next time you boot up a server.